much, Benoit, and to the ESMTB board for considering me for this colloquium. First of all, let me put my talk in context by introducing the general framework I will move in. Then I'll go to the specific case of this modeling cell orientation under stretch. Probably I'll be a bit more technical, I hope not boring. Now, as you know, I mean, all of you, the mathematical models that are developed for to describe cell behavior focus on the chemistry inside the cell. And this is okay, this is normal, starting from chemotaxis or the fact that cells need nutrients, chemical factors to grow, to produce ATP, or they activate, say, some overexpress some protein and underexpress other proteins. And after all, I mean, it's all related to gene expression. But more or less 20 years ago, the role of mechanics come into play and started growing this new field that is called mechanobiology, because it was found that it had strong consequences on cell behavior. And it can be split into parts, or if you want, in two steps. The first is called mechanosensing, and is the mechanism that the cells use to feel the mechanical forces. And there are several of them. I mean, they can do that by activating, opening ion channels and feeling, say, the shear stress of the flow, for instance, of interstitial fluid or of the blood flow, if we are talking about vessels, blood vessels, or through, say, focal adhesions that connect, say, the outside world, say, the extracellular matrix or the other cells, through integrin and caderins to the cytoskeleton. And the second part has to do with how the cell then responds to what they feel from the mechanical point of view, either directly, I mean, that if you pull on the actin fiber, of course, you have a response, which is a mechanical response. If you push the nucleus, you have a response, and so on. But probably the most important, interesting thing is how these mechanical cues are transferred into chemical patterns. To make an example, if you look closely at this picture here, the extracellular matrix connect to the actin fibers and microtubules through a bunch of proteins, the integrins that are here, for instance, and then there is this cluster of proteins, and among them there is tallinn. Tallinn is a molecule that has an helical shape, and so when it is pulled, this helix open up, exposing, say, activation sites, so it can activate then other phosphorylation, for instance, and other proteins. And so this is one way, one possible way in which then the mechanics is transferring to chemistry. And one can count the stresses, can measure the stress according to the size of the binding sites that are exposed. Okay, now why is that important? Because okay, no, going too fast. Okay, because there are a lot of diseases that in which the mechanics play a role, and this is a list, probably a partial list. So you see that there are a lot. Okay, now coming, for instance, to some examples: vasculopathies, the vessel walls, the vessel feel and adapt to shear stress and to pressure. For instance, they can dilate. For instance, in hypertension, this is classical, or can, say, reduce in size. They can even shunt. They can form aneurysm. They develop plaques and so on. Or going on, hydrocephalus and dementia is influenced by the say, an unbalanced interstitial pressure, too high pressure in the brain. Or there are a lot of fibrotic diseases that are related to the fact that too much extracellular matrix is produced. This stiffens the environment and feedbacking on the behavior of the cell that becomes pathological. And last but not least, cancer. Since the first moments of the development of cancer, we have what is called the cadherin switch, in which the cell lose the contact inhibition of growth, and they continue to proliferate when they shouldn't do that, for instance. So they don't feed the mechanics properly, the pressure properly. Then there are other issues like dysregulated MMPs, or again, excessive production of extracellular matrix that stiffen the stroma. In this respect, I found this experiment very nice by Alison Weaver, in which she seeded some cells on different gels with different stiffness. They are just endothelial cells of the breast. They form acini in a physiological situation, in which you have, say, the formation of this spherical structure, well polarized, with the basal side and apical side on the other side to say produce the milk in the lumen. But if you stiffen the gel in which you grow them, you lose the lumen, first of all. So it is called the hyperplastic transition. And then you lose also the sphericity of the acini. And if the stiffening becomes very high, about 1000 pascals, the cell undergo actually a mesenchymal transition. So they start moving and invading the substratum, the tissue. So you see, the same kind of cell in different environments behave, say, very differently from, say, benign, if you want, physiological, to very pathological. Okay, the other thing that was of a lot of interest, and probably the reason why mechanobiology blew up, is that comes with the development of tissue engineering. When you have to build a tissue from scratch, and what was found is that if you seed stem cells on substratum or different substratum, and you try to make a good environment for them, then they differentiate in different cells according to the mechanical properties of the substratum. When the substratum is very soft, it can become a neuron, then an endothelial cell, a fibroblast, a muscle cell, or an osteoblast. And for instance, you have to keep in mind that, as I mentioned before, in scar tissue in general, the fact that there is a lot of extracellular matrix stiffens up the environment. So it means that the tissue has not the same physiological mechanical property. So if the stem cells are directly injected into the tissue, there is the risk of generating something that is not, say, what you want. I mean, if you have a heart attack and you want to, say, cure your heart by injecting directly some stem cell, if that part is too stiff, you can generate osteoblasts. So it doesn't make any sense, for instance. And this is particularly true for neurons. That's why, though in principle, one could use stem cells to heal, say, neurological diseases, take the spinal cord, for instance, curing the spinal cord, and the presence of this environment that is not so native, and is not physiological, makes the things impossible. Okay? While, for instance, for endothelial cell, it's much better, the situation. Okay. Now, why am I saying all that? I mean, because my impression now is that all this blowing tissue, blowing subject is going on in a more or less empirical way, in the sense that the results that you find in the literature are very on the side of the experiments, and they report the result of the experiments, and there is very little modeling. And in some of them, there is no real understanding of the inmost mechanism that generates the result. So this is a subject that is quite new, so everything interested can choose its own particular application. I'm not saying that this is easy, but you know, it's an open subject. In this respect, what caught my attention a couple of years ago was a fact that in tissue engineering, you are trying nowadays to build patches to repair the heart. And from years, it is known, from centuries actually, that the structure of the heart is very complex because its role is to squeeze the blood out of the chambers. So the cells that make the heart need to be well coordinated and oriented so that when they contract, you have a pushing that is effective. Okay, and the direction of these cells differs from where you are, and also from how deep you are in the tissue. So the need in tissue engineering is to construct, say, oriented cells that are all aligned in the same direction. They are not growing at random. And the same thing was observed in arteries, where you see that in the intima, cells are not oriented, say, along the axis of the vessel, and not even perpendicular to the axis of the vessel, but they form a certain angle. Okay, it is thought that this might be one of the causes of the formation of the aneurysm. That is, if the cells are oriented in not a nice way, then you form a dilation of the aortic walls. Okay, it is not clear yet, but it is one of the possibilities. So actually, intrigued by that, in the 80s, people started doing experiments to investigate the response of cells to periodic stretches. Okay, because the heart, of course, beats every second, and also under the flow of the heart, the aorta also dilates every second, and there are other tissues that periodically, say, are stimulated, the lung, but also the bone when we walk. Okay, I'm not saying anything new. I'm saying that mechanics affects, say, the behavior of the cell or the growth of the cell and so on. I mean, if you don't practice, I mean, your muscle will just die out. If you go to the gym and practice, you pump up your muscles. Okay. So going to the experiment, this is what is done. You have a substratum, 2D, and the cells are seated on this substratum, usually in a non-confluent configuration. That is, they are just, say, not touching or barely touching each other. They're full of space in between them, just to eliminate, say, effect of cell-to-cell contact. And then this is stretched. In this picture, the size, the upper and lower sides are kept, say, fixed. They are clamped, so that you don't have any deformation in the y direction. Or the other experiment, they are left free, and in this case, you have a shrinking, say, in the y direction. And of course, in order to eliminate boundary effects, the experiment focuses on the central region. So what is seen is that when, for instance, in the first case, when you have clamped sides, the cell orient more or less perpendicularly to the stretching direction. In the second case, instead, usually what you have is that the cell orient at a certain angle. They tend to orient at a certain angle, In this case, it's larger than 45 degrees, smaller than 60 degrees in the average. Of course, there is some randomness because everything in biology is not deterministic. There are two things that I want to stress here that might be trivial. The first one is that, of course, there is no up and down. So you see some cells that are oriented along an angle theta, and other cells that are oriented downward with an angle that more or less is minus theta. Your distribution in minus pi over 2 is presents two peaks around, say, minus 50 something and plus 50 something. Okay. The second thing that I want to stress, and it's not evident in the picture, is that these cells are not moving. They don't have a head and tail polymerizing acting on one side and the polymerizing on the other side. They have just an elongated shape with a nucleus that is not spherical, is more or less ellipsoidal. And as we shall see in the following, with the structure, an inner structure that is oriented in this direction, in the orientation direction, what we call an orientation direction. The same thing occurs also in confluent conditions. For instance, the arterial walls. On the left, you can see cells that are oriented perpendicular to the stretch direction. Of course, it's much harder to see cells that are oriented in oblique directions because, you know, patchworking them is not very easy. But you can see here in this experiment by Takemasa that in these rhomboidal cells, you have the inner structure that I will discuss in a minute is oriented along theta and say minus theta. Okay. So it's the same. Now there are several things that are actually very surprising, and has to do with the fact that this behavior is very robust. Is robust with respect to the cell type. You can use several types of cells and you see the same thing: endothelial cells, epithelial cells, fibroblasts, myocytes, mesenchymal stem cells, osteoblasts. You see, there are cells that have different origin. There is only one cell that some time ago was found that does not behave in the same way. This is a nice example, macrophages. And the reason that for that was proposed, that the reason is that the macrophage has a different role than the cells on the left. They have to scout the environment. They have to move fast. Their motion is amoeboid, very soft. They don't have an inner cytoskeleton, which is, as say the cells on the left, fibroblasts. They pull a lot. They adhere to the substratum. Endothelial cells have, say, adhere to the extracellular matrix and so on. They have strong adhesion bonds and strong cytoskeleton. And in fact, this is what you see if you put in evidence, say, the cytoskeleton. You have the formation of this structure. They are called stress fibers. The stress fibers are bundles of actin filaments and microtubules in some directions. In this case, say more or less particular. These cells are osteosarcoma cells, but if you want to look at endothelial cells, more or less you see the same thing developing during, say, the periodic stretching. Okay, these fibers perpendicular to the thing. And probably you can appreciate that the nucleus is not spherical, it's a bit elongated in this direction. And in some cases, this also the cell becomes elliptical. Okay. But there are other things that actually are surprising. Is the fact that they are the phenomenon is robust with respect to substratum stiffness, as long as the gel, say the the substratum is stiff enough, larger than 10 kilopascal. The strain amplitude is large enough, 1–2%, and the stretching frequency is high enough. By the way, the fact that the stretching frequency is high enough rules out the fact that you are taking, if you take the specimen and you just pull it and you keep the deformation, you don't see any reorientation. Okay, that's 0 Hertz, in sense, or if it is very slow. And as we shall see, this is related to the fact that if the pulling is low, then cells have enough time to readapt and to release the stress. Okay, so what did we do to explain this phenomenon? The first model that I'm going to present develops in the field of continuum mechanics. So you have this specimen, you deform it so that the deformation gradient is diagonal. This epsilon xx, epsilon yy, and epsilon zz are the strain in the 3 direction. X, Y, and Z. And an important role will be played by what is called the biaxiality ratio. This number R, which measure say how much your specimen is shrinking in the y direction with respect to what is elongated in the x direction. Okay? The best collection of data that you have, you can find in the literature, are those by Livne that controls very with a great attention, say, this biaxiality ratio for fibroblasts. And you have that the experimental points seem to line up along the straight line. The straight line, however, in a very strange parameter space. That is, on the y-axis, you have the square of the cosine of the equilibrium angle, and on the x-axis, you have 1/r+1, where r is this biaxiality ratio. So why is that? This is what I will try to answer. To explain the situation, this point here corresponds to, say, the case in which the y sides, the upper and lower sides are clamped, so you don't have any deformation on the y direction. And this gives rise to cells that are elongating perpendicularly to the main stretching direction. This other opposite end is the one in which r is equal to 1, epsilon yy is equal to epsilon xx minus epsilon xx. And the other important point is this one, where you find, and here you have cells that are elongated, are oblique with 45 degrees. And the other point that is very, you see a lot of points, experimental points here, is the one in which, say, the shrinking in the y and z direction compensate the elongation in the x direction. Can be called the incompressible case. Okay. And in that case, you have that cells orient more or less with an angle of 57. I showed you this histogram that were, say, with a peak that was in that range. Okay, there are some experiments. And this slope is a given slope. It's minus 1.26 something. Okay. There are some experiments that have a negative R, which means that you are stretching in both directions. In this experiment, you have the cells on a disk, and you just increase radially, deform radially the disk, so that the cells feel a stretch, a strain both in the radial direction and in the circumferential direction, while experiments in this range for R greater than 1 are not done. Okay, so without going in, I mean, I don't want to be technical and give too much detail, what happens if you have a substratum, which is isotropic, and on the substratum, you put some cells that are oriented along the direction theta. And if you pull, say, just the cell along the stress fiber, of course, you have greater difficulties because you are stretching the actin filament than stretching them perpendicular to the stretch fiber, right? When you do that, what you have is that you lose the isotropy of the material. Your material becomes anisotropic. In general, what you know from continuum mechanics is that the elastic energy, if you are dealing with an elastic material, depends on some invariants. The usual invariants that are called the isotropic invariants, the trace, the determinant of what is called the Cauchy-Green strain tensor, and other quantities. This quantity I4, I5, and so on. What do they describe? Well, I4 and I5 describe how strong the material is with respect to stretching it along the stress fiber. I6 and I7 stretching perpendicularly to stress fibers, and I8 how the material responds to shearing them. Okay, you have to understand that in addition to stress fibers, there are the networking of the actin fibers, of the actin filaments, and so when you shear the thing, you have a response. Now, the thing that I want to show here, to stress in particular, is that when you compute all these quantities, in this case, these are just quantities that depend on cosine square. But for this last one, this I8, but because of symmetry, the energy must be even in I8. So this means that also I8 is a function of cosine square. So after all, for any general elastic energy, you can write it as a function of cosine square. And this already gives you an answer why you get that, say, in that diagram, cosine square is very relevant. Okay. In fact, if you have a function of cosine square and you try to find equilibria, trivially, you have that the equilibrium is given by the derivative of u times sine cosine. And so you have that when sine is equal to 0 or theta equals 0, you have that the cells would elongate along the stretching direction. When cosine is equal to 0, means that the cells will elongate perpendicularly to the stretching direction. And of course, you might have that this last term vanish, the u prime vanishes. And actually, this is the most important part that I'm going to discuss now. But in order to do that, I need to specialize the energy. So I will take, for instance, a very general polynomial, for instance, of second order in this invariance, or say what is called the Fung energy. Fung energy is used in to describe the behavior of a lot of biological tissue. And if you compute this u prime equals 0, you find that cosine square equal to something. Okay, and this something is a term here that depends on all these coefficients that multiply the invariance. These are the mechanical characteristics. In particular, say K44 is the stiffness that that describes how stiff the material is in stretching along the direction of the stress fiber, and so on. Okay, and this parameter lambda appears linearly, and in the small deformation case in the linear regime, this lambda is 1 over 1 plus r. So you have that trivially cosine square is a linear function of 1 over 1 plus r. That's it. And so you have an explanation of why there is this linear dependence of in the experiments by Lipton. And the bifurcation parameter is alpha. This alpha is here. This combination of mechanical parameters. Before discussing the bifurcation diagram, I want to stress one thing, that this oblique configuration depends on R, and R is the biaxiality ratio. So what happens is that if you stretch by, say, 5% your material along X, and it will shrink by 2% along Y, you have a certain R, is 250.4. Okay? If you stretch by 10% along X, then your material will deform by 4%. So you are changing the stretching, but your ratio in the experiment is the same. So that's why this is the first hint of why your result, your equilibrium, does not depend on the amplitude of your deformation. Okay? Because it depends only on the ratio of the deformation, not on the imposed stretch. So regarding the stability, what you have is that this is the range, the shaded area is the range that is tested experimentally. You have that up here is the equilibrium with theta equals 0, say the parallel configuration, which is not seen in the experiment because it's unstable. Instead, here you have the perpendicular configuration, perpendicular orientation, that is stable if this parameter lambda or 1 over 1 plus r is larger than 1 plus r over 2, something. I mean, this is not a small segment, it's a very important one, because as I mentioned, this value 1 is the one that corresponds to the experiment that is done a lot, that is the clamping experiment. Okay, so in that case, you have that the perpendicular orientation is stable. Otherwise, you have, say, the oblique orientation that is stable, the one that corresponds to this cosine square equals something. Okay. Okay, good. Then there are two bifurcation points, and they are supercritical. Okay. Now let's see, because of course you have the same, say, situation depending on a lot of parameters. Let's see what is the minimal number of parameters that is needed to describe the experiment. Assume that you want a model, and you consider in the model only the stiffness along the stress fiber. That is, you only have K44, and you forget about the others. If you do that, you find that alpha is equal to 1. And this is not what is seen in the experiment, because, as I mentioned, alpha is smaller than 1. I mean, the slope, if you have 1, you have a straight line that goes from this point here, 0, 1, to the end of this shaded area. Instead, the slope is steeper, negatively steeper. So alpha is 0.8, more or less. So in order to have 0.8, you need to have a certain relation between the parameters. So the minimal, for instance, that you can have is to forget about, say, the response with respect to the deformation perpendicular to the stress fiber. You can forget about this mixed term. This is too technical. But K88, that is the response to shear, is important. Okay, and you can also say that K88, the parameter related to the response to shear, has to be more or less 1/5 than the response to pulling along the stress fiber, and you can get the fitting. You get a very easy fitting. What happens instead if you forget it? You forget K88, but you keep the response perpendicular to the stress fiber. In that case, this number is greater than 1. It corresponds to the black line here. Now, is that possible? This is not discussed in the literature. It's never mentioned, but and it goes with the question of whether the slope found by Leibniz is universal. Okay. If you look at this experiment by Wang, this is what happens. This is done on endothelial cells. In the free case with R equal to 0.34, you have that the maximum, say, the mode of this distribution is around, say, 70 degrees. So you are here, and you have an oblique configuration. In the clamped configuration, this is what you get. This is the picture that I showed before. And you have that the maximum is more or less 90 degrees. But if you look closely, it's not really 90 degrees. It's something less, in some sense. It's 85 degrees. So it seems, but this is my explanation, because one in words says that the orientation is perpendicular, that is nearly perpendicular. So it might be that it's this point here. So this case, if we investigate it more in detail, might say that for fibroblasts, you have a slope that is 0.8, and for endothelial cells, it's a little bit large. And so it might be that for endothelial cells, including, for instance, K6s, is important, while for fibroblasts is more important the response to shear. Okay, so interpreting this result, you get an information of what is the mechanical behavior of your actin cytoskeleton to pulling and to shear. Okay, this is what you can get from, say, the study of the equilibrium of your model. What about the temporal evolution? There are some data on how the cell orient in time to go toward the equilibrium values. This is still found in the paper by Leibniz. You have different cells, in this case 6 cells, that starts from different initial orientations, and they all go towards, say, minus, in this case it's minus 60 something and plus 60 something. Okay, and this instead is what happens when you start more or less with an angle that is close to 20 degrees, and because you R changes, you go toward different equilibrium. And for them, those cells, you have that the equilibrium is reached after some, say, half an hour or 1 hour. This is the order of magnitude in this aspect. So how can you model that? You can do that by resorting to a Lagrangian principle, to have the virtual work, by saying that the cells tend to minimize the virtual work. That is, to change its internal angle to reach the equilibrium. And so the theta over forgetting about inertia, because I mean we are talking about something that lasts, I mean, half an hour, so inertia can be neglected. You have just the theta over dt is proportional to the derivative of u with respect to theta. And trivially, the equilibrium is found back when this derivative is equal to 0. That is what we studied before. And if you compute that, this is what you have. It is not too far, actually it's very close to me, it's not too far from the experimental result. This is when you start from different angles, and this is when you start from the same angle, 30 degrees, and you change R. And you go toward the equilibrium more or less in the same time. Okay, so we were pretty satisfied also with that. And now the next step is to try to understand, say, the robustness of this result with respect to the different features of the experiment. Okay, the first one I already discussed a bit, dependence on the strain amplitude. I told you that the equilibrium does not depend on the strain amplitude as long as it is large enough. but the timing to reach the equilibrium does, in the sense that the stronger you pull periodically your substratum, the faster you get to the equilibrium. Okay? This, in some sense, this can be already guessed by this equation, because in this equation you have a term that is, say, proportional to 1 plus r, and r is fixed. A term that depends on theta and on r, lambda and r are more or less the same. But there is this term here, epsilon xx squared. So it means that if you increase epsilon xx, the characteristic time, this tau, if you increase epsilon xx, will decrease. And it will go like epsilon xx squared. Okay? So let's take some data and to compare. So it means that, for instance, if you start with a strain of 50%, 15%, and you say lower to 10%, 2/3, the square is 4/9, and so you have the timing should becomes 9/4, more or less doubling, and this is what you get. So the comparison is good, and this in the graph is more or less compares well with these 3 data, not too much. But if you decrease further, unfortunately, the comparison is not so good. If you have, say, the strain to 5%, you should say the timing should be 4 times, and this is not the case. It is something like 3 times, not 4 times. Okay? To tell you the truth, actually, a timing that goes like 1 over epsilon xx squared would be much nicer, because one could say that when epsilon becomes very small, then the times become too large compared to the timing of the experiment, and so that's why we don't see anything. And in particular, randomness will destroy everything, as we shall see. But this is not the case. So this part here, what happens for small strain should be investigated more. What happens instead when you change the frequency? Also in this case, the timing to go toward equilibrium depends on the frequency. There is a plateau region in which the timing is more or less constant, and then the timing goes up when the period of oscillation increases. And by the way, this graph is in a log-log plot, so this timing can grows considerably. Okay. Now the thing is that this feature cannot be described by the model that I was introducing till now, because you need, say, an intrinsic time, to introduce an intrinsic time, because the elastic model has the property to adapt immediately to the deformation. That is, you deform cyclically, and the material will respond at the same time. Okay, and instead, of course, there are several reasons that this does not hold. So this model is not good enough. The reason for adapting to have, say, having an intrinsic time are related to the fact that the cytosol is not elastic, it's viscoelastic, more viscous than elastic. The actin cytoskeleton is viscoelastic, behaves like, for instance, a void calculator. And more importantly, addition bonds changes the turnover. There is a turnover in it. There is a finite lifetime of the interim bonds. When they are stretched, they just rupture and they form new bonds. And the characteristic turnover time is of the order of, say, minutes, I would say. And if you compare this timing with the period, the threshold of the period of oscillations for which this phenomenon is observed, there is some correlation, in the sense that if you stretch with a period of 1 minute, you don't see anything. Why? As I said before, probably because you are allowed, have allowed your cell to reorganize the addition bonds and to release the stress. Because the final picture, the final message is the cells want to minimize the energy, the elastic energy that it feels. So in order to do that, we have to introduce viscoelasticity. I will not go into detail in that. I will just write the model in integral form and discuss it a bit. In this constitutive equation, what you do is to compare the strain at present time with the past strain through the elastic tensor that the cell had at past time tau, and you weight this contribution with a relaxation kernel. Now, if you take this relaxation kernel to be an exponential, then you can rewrite this constitutive equation in integral form, which is probably more familiar to most of you. And it's this one. It tells you that, say, the derivative of the stress times this relaxation time plus tau plus t is related to the derivative of the strain. This is called the Maxwell model. And then this stress here is found in the equation given the evolution of the angle through the derivative of the work. This is more or less related to work done by the cell. Okay, so what happens if you compute, you solve that system? You find that if you change the frequency, you go to the same equilibrium. This is theoretical. Can be theoretically proved classically, but you have that for large frequencies, you have that the time to go there is much shorter than when you lower the frequency. If this is too low, you don't see anything actually. And if you compute the timing to reach equilibrium and compare with the experimental data, the fitting is a mid plus without bias, and it's pretty good, and you have the same trend. And this last triangle relates to a more or less to a transition that gives a region in which you have a certain velocity, constant velocity, to reach equilibrium, to another one in which the velocity is incredibly small. Okay, good. Last thing I want to address now is randomness, because till now, my model is deterministic. And if you all know, I mean, nothing in biology is deterministic. And in fact, the graph that I showed you from the beginning are histograms presenting the frequency of finding a cell in a certain range of angles. So you have a distribution function over the angle, okay? So this first graph on the top reports how this frequency changes with time. Initially, you have more or less a uniform distribution, the yellow graph. Then after 1 hour, you have that a pinging up starts around 50, 60 degrees. And with time, this picks up more, and most of the cells are, say, oriented with an angle of 60, 70 degrees in this interval here. These two graphs on the bottom instead focus on the equilibrium distribution that you get after some time, changing, say, the amplitude, say, eventually, the one that you get eventually. And you have that at 2%, your distribution is, say, a broad variance, if you want. And if you increase the amplitude, then your distribution is very peaked, around, say, 90 degrees. This is 90 degrees. is the case in which the cells orient perpendicularly to stretching direction. And this instead has to do with what happens when you change the frequency. Okay? When you change the frequency, again, you have a picking up of your distribution function. So in order to describe that, we used a probability density with some symmetries, the symmetry that I was studying before, theta minus theta, pi minus theta are the same. And you can write a Fokker-Planck equation there, okay? Where sigma is taking care of the randomness, and these drift terms take care of the fact that the cells tend to go toward the minimum of energy. And from that, you can trivially compute the distribution function, and which is an exponential of the energy, of the elastic energy, so that the minimum of the energy corresponds to the maximum of this equilibrium. But the most important thing that I want to show you is the fact that this sigma bar at the denominator has a contribution of epsilon, the strain, so that immediately, if you increase the applied strain, what you get is that this decreases. Okay, so you have a picking up of the distribution like in the graph. So this is a result of the evolution in time here of our orientation compared with the experimental one. And this instead is how the distribution function changes with the amplitude in the case in which the minimum is, the maximum, sorry, is 90 degrees, r equals 0, and this is when you stop. I mean, this is pretty good, at least to us. Last thing, just to say a few words, you can look also at the same problem as a control problem, and I think that this is what the cells actually do, in the sense that they choose the new orientation, trying to minimize some functional, okay, and the functional is related, for instance, to the energy. So if you take this G, the energy, then you have the same Fokker-Planck equation that I described before. If you take, for instance, another G, say the classical square, the distance between the new angle and the optimal angle, the equilibrium angle, you have a different equilibrium, a different drift term, which more or less, if you compare, give the same nearly the same distribution. Okay. Okay, so that's it. So what is open now, and we are trying to address this problem. The first thing is to address very closely the fact that we don't have an elastic model, we have a viscoelastic model, and so we would like to introduce that into the kinetic model, and to explain this graph by Mao. We have some, say, discussion, introductory discussion also in the paper that I mentioned, but it needs to be say investigated more. And the other thing that we are trying to do is to introduce the effect of the substratum, and say because it is found that when the substratum is too soft, then this reorientation does not occur. And you have, say, that instead you find, say, cells either elongated along the stretching direction or perpendicular to the stretching direction. And we do that by discretizing the cell as in a tensility way. That is, by elements that are done by springs and dashboard, and each element here describes mechanical characteristics of bond remodeling, elasticity of the substratum, and so on. And with that, I will thank you for your attention, and I will question.